All right, so we are going to continue with the second example, which is the equilibrium between sulfur dioxide and oxygen gas, where we get a product of sulfur trioxide. Okay, so our volume, right, is given as 1 dm cube flask at 500 degrees Celsius. Okay, for the temperature wise, right, we don't have to be too bothered, because for any particular question, temperature is going to stay constant most of the time. All right, so if temperature doesn't stay constant, then we cannot use the same Kc to do our calculation. All right, so most of the time the temperature will stay constant. Okay, so we note that we are given 0.6 mole of sulfur dioxide and 0.2 mole of oxygen, and at equilibrium, right, we have 4.8 moles of sulfur trioxide, right? All this amount, right, number of moles are in equilibrium, at equilibrium, all right? So given all this at equilibrium, we do not have to draw the ice table. We simply have to substitute these values divided by 1 dm cube into the expression. So that is exactly what we're going to do. And we should get a value of Kc as 320 per mole dm cube. All right, if you've forgotten how to calculate the units for Kc, please go back to the video on part 1. Then from there, we will teach you how to calculate the units from the expression. Okay, B, how many moles of oxygen gas must be added into this flask to increase the amount of sulfur trioxide to 5 moles? All right. Okay, so since we are not told what's the amount, in fact, that is the thing that we're supposed to find, right? The number of moles that we have to increase oxygen by. Okay, to get the equilibrium from 4.8 moles to 5 moles per dm cube. Right, so the change, very simple. We can see that the change here is positively 0.2. So if the product has to increase by 0.2, the reactants all have to decrease by the corresponding stoichiometric amount. All right, because for sulfur dioxide and trioxide, it is the same amount, but for oxygen, it is half the amount of sulfur trioxide. Okay, so you can see that's the reason why it is minus 0.2 and minus 0.1. So with that, we now have the expression for x, all right, at equilibrium. Okay, so again, we're going to substitute all these values into our Kc, which we have already calculated to be 320. All right, once we sub that in, we just need to solve for x, and the amount that we need to add to 0.2 moles of oxygen is 0.388. All right, in order to raise our equilibrium concentration of sulfur trioxide to 5 moles. Okay, I think the question here will be the amount at equilibrium, okay, to 5 moles. All right, so that's for the second example. Okay, the third example is the calculation involving Kp. Okay, so instead of concentration, now we're gonna look at a example on Kp. All right, gaseous mixture. Okay, so we are told that the equilibrium, right, has 0.5 moles of sulfur dioxide, 0.2 moles of oxygen, and 5 moles of sulfur trioxide. Okay, and we are also told that the pressure, right, in the flask is 8 times 10 to the power 5 Pascal. Okay, so the first thing is we need to calculate the partial pressure. Okay, so in order to calculate partial pressure, we just need to take the mole fraction multiply by the total pressure. So total pressure is actually given here. All right, all the number of moles are given by the question. Okay, so all we need to do, find out the total number of moles of gas, take the mole fraction, multiply by total pressure to get the partial pressure of each of the gas. All right, hope you got that. That was relatively straightforward. Part B asks us to calculate the equilibrium constant Kp. So we basically just take all the values that we've calculated in part A and we substitute it into the expression and press our calculator and we will get our answer. All right. Okay, so that's it for the third example.